right? So this is the basic formula for moment of inertia. I is equal to sigma mi ri square. So if you have a system which is a collection of discrete particles means separate particles, then you can calculate it this way. Moment of inertia, m1 r1 square plus m2 r2 square, so on up to mn rn square. But if there is a continuous mass distribution, like any real life object, okay, it will be a collection of many particles which are distributed continuously, one immediately next to another, and so on. Can one of you tell me how to write the formula for moment of inertia for a continuous mass distribution? What does sigma change to?
Integral r square dm.
Okay, sigma changes to integral mi. Okay, in the formula for moment of inertia, mi is mass of the ith particle. In a continuous mass distribution, you will just call it as dm, mass of an element. And ri square, ri is the distance of the ith particle from the axis. So here you will just take distance of the element from the axis and square it. So if you want to find out the moment of inertia of a continuous mass distribution, this is how you are going to do it. Okay. Let's apply this formula and derive the moment of inertia of a uniform rod. Moment of inertia of a uniform rod about an axis perpendicular to the rod and passing through one end of the rod. Okay. Assume the mass of this rod is m and its length is L. Imagine an axis, okay, passing through one end of the rod and perpendicular to its length. So this is the axis about which we want to derive its moment of inertia. What is moment of inertia? I told you, no, it is rotational inertia. How reluctant, okay, or how resistant a system is to a change in its rotational state. That is what is moment of inertia. So we need to find out that for this rod. A rod is a continuous mass distribution, and for continuous mass distributions, moment of inertia is calculated as integral r square dm. Or you can do it like this. Take one element of the continuous mass distribution. One small element will contribute small moment of inertia. So you can write it as r square into dm. And then you integrate that to get the total moment of inertia. You integrate the small moments of inertia contributed by each element. Okay. So we will first consider an element of this rod, maybe from here to here. Since it's a small element, it'll have a small mass dm. Assume its distance from the axis is r. Why do we care about its distance from the axis? Because moment of inertia depends on that. Okay, it depends on how far the particle is from the axis. Therefore, the moment of inertia of this one particle or one element can be written as r square into dm. Mass multiplied with the square of the distance. Fine. Now, if you want the total moment of inertia of this rod, you will have to do integral r square dm. Can one of you tell me, before we integrate r square dm, what do we have to do? Or in order to integrate r square dm, what do we have to do?
Dm you have to write in terms of r.
Okay. We need to express dm in terms of dr. Okay, if you remember, we had done something similar while deriving the position of center of mass also for different systems. Okay. Continuous mass distribution. If you have to integrate x dm, you need to express dm in terms of dx. Okay. Similarly, in moment of inertia, you'll have to integrate r square dm. So you will need to express dm in terms of dr. Aishwarya, can you tell the meaning of dr? Generally, what does dr mean, or dx or dy? What does it mean? Rishi?
Sir, it's the small length which is
Okay.
taken.
Okay. See, d stands for change. Okay. dr is like delta r only, but a very small change. So dr means small change in r. Now we have taken r as the distance along the x-axis, or I can say r is the distance of the element from the axis about which we want to find out the moment of inertia. Then dr should be the change in r for that element. So when you go from one end of the element to the other end, there is a small change that is going to occur in the distance from the axis. So the length of the element itself becomes dr. Okay, because r is along the rod, along the length of the rod. The length of the element is also along the length of the rod. So element length itself is dr. Okay. Can one of you tell me how to express mass of an element in terms of length of the element? While deriving position of center of mass, if we or whenever we had to express the mass of an element, what did we do? We first look at what kind of mass distribution it is. Yusuf, what are the three different kinds of mass distribution we came across? What are the three different types of mass distribution we studied? Okay. Vanilla, tell me, what are the three different mass distributions we studied? You unmuted, but I don't hear anything from your side. Anyway, the three different types of mass distribution we came across are linear, areal, and volumetric. Okay. One of you tell me, what kind of mass distribution is a rod? Is it linear, areal, or volumetric?
Sir, it's linear.
It's a linear mass distribution, correct. And for linear mass distributions, how do we relate mass of an element to length of the element? Okay. For linear mass distributions, we use something called linear mass density. See, generally, density is what relates mass to the space occupied. So linear mass density relates mass to the length occupied. You can write length occupied as dx, or you can write it as dr also in this case. That's all, which is also equal to total mass by total length. So mass per unit length. So you can write dm is equal to lambda into dr, where lambda is total mass by total length. We'll substitute it at the end. Okay, this is how you get dm in terms of dr. So remember, not just in this case, in any case, if you are required to find out the mass of an element or to express the mass of an element in terms of something else, you should first look at what kind of mass distribution it is. If it is linear mass distribution, mass of the element is lambda multiplied with length of the element. If it's areal mass distribution, mass of the element is sigma, areal mass density, multiplied with area occupied by the element. If it's volumetric mass distribution, then it is normal density into volume occupied by the element. Okay. So dm is equal to lambda dr. We'll substitute that in the integral. Therefore, the moment of inertia of the rod becomes integral r square into lambda dr. Lambda is mass per unit length. We call it linear mass density. Now I told you that the rod is uniform, means the density everywhere will be the same. So you can put it outside the integral. It's a constant. And you will be left with integral r square dr. Can one of you tell me how much is integral r square dr?
R cube by 3, sir.
Okay. So it becomes lambda r cube by 3. And we want to find out moment of inertia of the entire rod. If you want to cover the entire rod, see, r is the distance of the element from the axis, no? What is the distance of the first element from the axis? 0. What is the distance of the last element from the axis? L, the length of the rod. So the limits for r will be from 0 to L. You substitute those limits. Lambda is mass by length. And let's substitute those limits. L cube by 3 minus 0 by 3. That is L cube by 3. One L gets cancelled. You will end up getting ml square by 3. Okay, this is a very useful result. We'll be using it very frequently. Can one of you tell me for which system we found out the moment of inertia?
Uniform rod.
Uniform rod, correct. About which axis? How was the axis taken? Axis,
Perpendicular to the rod.
perpendicular to the rod, passing through one end of the rod. Okay, so this is the moment of inertia of a uniform rod about an axis, about or with respect to axis also you can tell. Okay, about an axis perpendicular to the rod and passing through one end. Okay, now whenever you derive a formula for moment of inertia or you remember a formula for moment of inertia, you should also remember about which axis that moment of inertia is calculated. Okay, let's see how it matters. Consider a simple two-particle system. Let's say this is 1 kg. This is also 1 kg. Assume the total distance between them is some 4 meters. Okay, roughly. Consider an axis like this, from which this mass is at 2 meters and the other mass is also at 2 meters. One of you quickly calculate and tell me the moment of inertia of this system. You don't have to use a pen also. It's a two-particle system, that's all. So m1 r1 square plus m2 r2 square. How much is the moment of inertia about this axis? Yusuf, how much will it be? Okay, see m1 r1 square plus m2 r2 square. m1 and m2 are masses of the particles. r1 and r2 are distances of the particles from the given axis. Why is it taking so long? Rishi, how are you calculating?
Repeat your question once.
I want the moment of inertia of this system. Okay, let it be. Let us discuss. So this mass you take as m1, then this distance becomes r1. If this mass is m2, then this distance becomes r2. So m1 r1 square, 1 into 2 square, 2 square is 4. Again m2 r2 square, 1 into 2 square, again 4. 4 and 4, total moment of inertia about this axis is 8 kg meter square. Okay, it will be 8 kg meter square. Fine. For the same two-particle system, let's take a slightly different axis now. This one. What about the distances? Distance of this mass from this axis is 1 meter. Distance of the other mass from this axis is 3 meters. Okay. Aishwarya, can you unmute?
Yes, sir.
How much does the left side particle contribute to moment of inertia about this axis?
So 1 kg meter square.
Yeah, mass is 1, distance is also 1. So mr square will be 1 kg meter square. How much does the right side particle contribute?
So 9 kg meter square.
If you add them both, it becomes 10 kg meter square. That is the moment of inertia about this axis. And 8 kg meter square is the moment of inertia about this axis. So what this clearly proves is that moment of inertia can change from axis to axis. For the same system, it can change from axis to axis. That is why whenever you derive a formula, or even if you try to memorize a formula for moment of inertia, you should also remember about which axis it was calculated or derived. So for a rod about one end, it is ml square by 3. Okay, about an axis perpendicular to the rod passing through one end, it is ml square by 3. Okay, so remember how we derived this? We took an element of the rod, dm, which was at a distance r. That dm contributes a small moment of inertia, r square into dm, or dm into r square also you can write. Then if you integrate the small moment of inertia contributed by one element, you will get the total moment of inertia of the rod. That is what we did. And we wanted to cover the entire rod. So the limits were from r is equal to 0 to r is equal to L. Fine. Let's take another situation. Moment of inertia of a uniform rod about an axis or about its perpendicular bisector. What do we mean by perpendicular bisector? A line which passes through the midpoint and is perpendicular to the rod. So maybe somewhat like this. Our aim now is to derive the moment of inertia of this rod. Rod mass is still m, length is L, about this axis. Okay. Can any of you tell me some ideas how to do it? No ideas. Okay. So this means that we need to work on the previous derivation a little bit first. Fine. We derived the moment of inertia of a uniform rod about an axis perpendicular to the rod passing through one end. Let's solve some problems based on that first. The formula we derived is ml square by 3. Remember that at least. Okay, for this axis, the moment of inertia is ml square by 3. Suppose the mass of this rod is some 3 kg and its length is 2 meters. Okay. Tell me its moment of inertia about this axis. Calculate this quickly, all of you. How much is the
Sir,
moment of
4
inertia?
kg meter square.
Okay, we'll see. Yusuf, what is the formula we derived for moment of inertia of a rod about this axis? The formula we got is ml square by 3. Okay. Applied directly 3 into 2 square divided by 3. The answer becomes 4 kg meter square. Fine. Now try this, all of you. For uniform rod, it is ml square by 3. That is fine. Suppose you are given a non-uniform rod. Okay, you don't even know its total mass. Let's say the length is 2 meters. Okay, and the density varies from point to point. It's a non-uniform mass distribution. And how does density vary? Let's say density varies with the x coordinate as lambda is equal to 2x. What does that mean? When x is equal to 0, lambda is 0, means the particles are very light. Lambda means linear mass density, okay? Mass per unit length. You can write it as dm by dr if you want. You can also write it as dm by dx because the length is along the x-axis. Okay. So when x is equal to 0, lambda becomes 0, means the density at this end is almost 0, is equal to 0. As x increases, means as you move to the other particles of the rod, the density increases, means particles become heavier and heavier. So this is a non-uniform rod of length 2 meters. Derive its moment of inertia about the axis that is shown in the diagram. Do this, all of you. You can ask me if you have any doubts. The linear mass density is given as a function of x. Total length of the rod is 2 meters. Carefully derive its moment of inertia. I'll give you a start also. You have to take an element first. Assume its mass is dm. Distance from the given axis, you can take it as r. And because the rod is along the x-axis, r will be same as x. Okay. And the length of the element, you can call it dr. You can call it dx also. Okay. And what is the formula for moment of inertia? The small moment of inertia contributed by one element is r square dm. The total moment of inertia of a system is integral r square dm. Okay. Apply this and tell me the moment of inertia of this rod. Right. So I got two answers as 8 kg meter square. I think that is correct only. So to integrate r square dm, we need to express dm in terms of dr. Dm is the mass of the element, dr is the length of the element. Mass and length of an element are connected through linear mass density lambda. So here lambda is given as 2x. So you can write 2x, that is lambda, is dm by mass of the element by length of the element. So dm is equal to 2x dr, but x becomes another variable. So let's write it in terms of r itself. In this diagram, as you can see, x and r are the same. Okay. So the moment of inertia can be calculated as integral. In place of r square, I'm taking x square because r is same as x. And in place of dm, I am writing 2x dx. Okay, 2 is a constant, keep it outside the integral. X square into x becomes x cube dx. And integral x cube dx is x to the power of 4 divided by 4. Now, to cover the complete rod, x should vary from 0 to 2 meters. Okay, so the limits for x will be from x is equal to 0 to x is equal to 2. That's all. Substitute upper limit first. 2 power 4 is 16 by 4 minus substitute lower limit 0 power 4 by 4. So this becomes 8 kg meter square. Correct. Okay, hope this is clear to all of you. If you have any doubts, you can ask. Okay, so first case, we applied the formula for a uniform rod, for moment of inertia of a uniform rod about one end perpendicular to itself, ml square by 3. We got the answer as 4 kg meter square. So if a rod is given and an axis is given passing through one end perpendicular to it, you can easily tell the moment of inertia now. If a non-uniform rod is given also, you can integrate and find out. Now let's go back to that derivation. Moment of inertia of a uniform rod only, but about perpendicular bisector is what we want to do now. Can any of you give me an idea what or how shall we proceed? To derive its moment of inertia.
Sir, I equal to integral r square dm.
Okay, you want to use the basic formula. Fine. Why not? It can be used. See, this is a continuous mass distribution. And for continuous mass distributions, we know I is equal to integral r square dm. Okay, let's try this way first. We need to choose an element dm, which is at a distance r from the given axis. This time axis is passing through the midpoint of the rod. So from midpoint, the distance is r. Okay. And needless to say, the length of the element becomes dr. Okay. Now you want to integrate r square dm. For that, you will have to write dm in terms of dr. I'm not going to repeat it. It's a linear mass distribution. So dm can be written as lambda dr. I'm writing it off directly, where lambda is mass per unit length, to m by L. That's a constant, we'll put it outside. Because the rod is uniform, no? Mass per unit length will be same everywhere. You will be left with integral r square dr. And integral r square dr, I'm writing the result directly, is r cube by 3. What you now have to tell is the limits for r. We need to cover the entire rod, means we need to cover every element starting from here. This is the initial value of r to here. This is the final value of r. One of you tell me what limit shall we take for r?
Minus L by 2 to L by 2, sir.
Good. You have to take minus L by 2 to plus L by 2. Because this time r is being measured from the midpoint. Right side is positive, left side is negative. So left side, the rod extends up to minus L by 2. Right side, it extends up to plus L by 2. So limits will be from minus L by 2 to plus L by 2. So you can express moment of inertia as lambda by 3 is also constant, I'm putting outside. R cube, if you substitute upper limit, it becomes L by 2 whole cube, that is L cube by 8, minus, substitute lower limit, minus L by 2 whole cube is minus L cube by 8. So effectively it becomes lambda by 3 into L cube by 8 plus L cube by 8 is 2 L cube by 8. And what is lambda? Mass by length. So one L value gets, one L gets cancelled. 2 and 8 go 4 times. You will be left with ml square by 3 into 4 is 12. Therefore, the moment of inertia of a uniform rod about its perpendicular bisector is ml square by 12. Very, very important. You need, we'll be using this very frequently, so you need to remember. Is the derivation clear to all of you? I'll tell you another way also to derive. Okay. So here we derived the moment of inertia of this rod about this axis using the fundamentals, integral r square dm. Basic formula for integration we used. Sorry, basic formula for moment of inertia we used. The other way to derive this is to consider the rod as a combination of systems. You are given a rod of mass m, length L, okay? But you were asked to find out its moment of inertia about a perpendicular bisector, not passing through one end or something. But before this derivation, we had already derived moment of inertia of a uniform rod about an axis passing through one end perpendicular to it. Now this given system can be considered as two separate rods like that. One rod from here to here, another rod on the right side. Okay. So the total moment of inertia about this axis can be taken as I1 plus I2. What is I1? Moment of inertia of the left side rod about this axis, left half of the rod. And I2 is the moment of inertia of the right half of the rod. Okay, you can just treat the two halves separately. Why take it like this? Because we know what is the moment of inertia of a uniform rod about one end perpendicular to it. So the total rod of mass m, length L is being split into two separate systems now. Let's consider only this system first. The right half of the rod. Just a moment. Okay. Rishi, tell me, what will be the length and mass of this right half of the rod?
M by 2 and L by 2.
M by 2 and L by 2. Okay. Its mass is M by 2. Its length is L by 2. The axis that you see here is passing through its end and is perpendicular. Generally, when axis passes through end of the rod and is perpendicular, the formula for moment of inertia is ml square by 3. That's the first formula we derived today. Here we'll have to put mass as m by 2, length as L by 2, square it, divided by 3. That rod's mass and that rod's length we have to substitute. This becomes m by 2 into L square by 4 whole divided by 3. 2 into 4 is 8, 8 and 3 is 24. So this becomes ml square by 24. So for the right half of the rod, the moment of inertia is ml square by 24. For the left half of the rod also it will be the same, no? Because this half also has a mass m by 2 and a length L by 2. The axis is still perpendicular to the rod passing through one end. So that left half also will contribute ml square by 24. Right half ml square by 24, left half ml square by 24. Therefore, total moment of inertia is 2 times ml square by 24. That is ml square by 12. And that is what we derived using integration also. Okay. Are both ideas clear to all of you? The integration method and treating it as a collection of two separate rods, that method. Aishwarya, did you understand?
Yes, sir.
Okay. Let's solve some problems based on this formula also. But let's go back to where we first encountered this quantity called moment of inertia. We tried to derive an expression for kinetic energy. Okay. In pure rotation, when a system rotates about a fixed axis, we tried to derive an expression for its kinetic energy. And when we tried to derive the expression for kinetic energy, we got it as half I omega square, where I is moment of inertia about that axis. So in rotation, if you want to calculate kinetic energy, you need to first calculate moment of inertia and you need to know how fast the system is rotating. Okay. So remember this formula also, and this formula is analogous to half mv square. See, in translation, the formula for kinetic energy is half mv square. That's what we have been using all these days also. M is mass, v is the speed. When it comes to rotation, in place of mass, see, mass is a measure of inertia. In place of mass, you'll get moment of inertia. Moment of inertia is a measure of rotational inertia. So in place of mass, you will get moment of inertia. And in place of speed, you will get angular speed. Okay, V changes to omega. That is how you calculate kinetic energy in rotation. Okay, let's solve a few problems based on this. First, rod of mass 2 kg, length 6 meters, rotates about one end. Okay, that means it rotates about an axis passing through one end perpendicular to the rod. So if this is the rod, this is the axis of rotation. Okay, and how fast it is rotating? Rotates about one end with angular velocity of, say, 10 radians per second. Okay, that is how fast it is spinning. Derive its kinetic energy. It is spinning around this axis. Okay, I got one answer as 1200 joules. Aishwarya, can you unmute? We'll discuss.
Yes, sir.
So, how is the rod moving? What kind of motion is it executing? Translation or rotation?
A rotation, sir.
It is rotating. Okay, pure rotation. The axis is not moving. The rod is rotating around that axis. Okay. Then what is the formula for kinetic energy of an object which is rotating?
The half by omega.
Half I omega square. I is moment of inertia, and we know moment of inertia can vary from axis to axis. So you need to remember I should be taken about axis of rotation, not some other axis. Okay. Now the axis of rotation is clear in the diagram. It's passing through one end of the rod and is perpendicular to it. Aishwarya, tell me, what is the formula for moment of inertia of a rod about this axis? Uniform rod.
Sir, ml square by 3.
ml square by
3, sir.
3. Okay. If you substitute, mass is 2 kg, length is 6. So 6 into 6 divided by 3. 6 fourths. This becomes 24 kg meter square. That's all. Then you just have to substitute in the kinetic energy formula now. So it becomes half. I is 24. Omega is 10 and you square it. 24 by 2 is 12. So answer will be 1200 joules. That is the total kinetic energy in this rod. Okay, so this is one of the ways in which we make use of moment of inertia. Is this clear to all of you? Yusuf, did you understand? Okay, Rishi, is it clear?
Yes, sir, I got the answer.
Okay, good. So remember, whenever you see rotating systems, automatically this quantity called moment of inertia should come to your mind. Okay, everything you calculate about a rotating system will be in terms of moment of inertia only, not just kinetic energy. You will see. Okay, there are a lot of other things that you can tell based on moment of inertia. Okay. Now consider a rod which is inclined at an angle like this. Okay, this is slightly tricky. The rod's mass is m, length is L, okay? But the rod makes an angle alpha with this axis. It's not perpendicular, okay? Or you can say axis is passing through one end of the rod, but it's not perpendicular to the rod. Axis makes an angle alpha with the rod. The aim now is to derive the moment of inertia about this axis. Can any of you give any ideas what can be done? How to derive moment of inertia of this rod about this axis?
Sir, is there any result that which says that when it's perpendicular that the moment of inertia is maximum or something? So that when we take that into consideration, we'll know that it'll be lesser than when it's perpendicular to the ground.
So what if it is less? You need to get the exact value, no? Just knowing that it is less won't help you. Okay. Yeah. And okay. Because you asked me that question, let us have that discussion also. See, what he is asking is, can we tell anything, or can we tell that the moment of inertia about a given axis for a rod will be maximum when the rod is perpendicular to the axis? That is what he asked. Okay, let's discuss that. Suppose the rod is placed like this. Mass is m, length is L. Means the last element of the rod is at a length L from the axis. And in between also there are particles. Not all elements are at that distance, but the last element is at that distance. Okay. Now this same rod, keeping one end there itself, if you rotate the other end like this, okay, maybe rotate some more also. Length is the same, total length is the same, but it's rotated now. Now you visualize the axis. Let us extend this axis a little bit. Tell me, is the last element still at a distance L, or is it closer or farther?
No, it's not.
It's closer. This distance is less than L now. So effectively what has happened is mass has come closer to the axis. Okay. Compared to this position A, in position B, the particles are closer to the axis. Total mass is the same, but the particles have come closer. If particles come close, okay, moment of inertia is summation of mr square. So m1 r1 square plus m2 so on up to mn rn square. Particle mass is not changing, but some particles are coming close to the axis. Rishi, you only tell me now. If particles come close to the axis, what happens to r values, r1, r2, and so on? Will that increase or decrease?
Sir, it will decrease.
Decrease. As a result, what will happen to moment of inertia?
It will decrease.
It will also decrease. Okay, so did you get the answer to your question?
Yes, sir. So when it is perpendicular, it is the maximum, right?
Ha. Because in that orientation, the particles are far from the axis. If it makes an angle alpha like this, the particles are closer to the axis. So you are decreasing the distance, then you will be decreasing the moment of inertia. Okay. Anyway, that still does not give us an exact expression for moment of inertia. You just know that the answer should be less than ml square by 3. But how exactly can you derive the moment of inertia of this rod? Now, see, the axis is not perpendicular to the rod. It's neither passing through its center perpendicularly, nor is it passing through the end perpendicularly. It's passing through the end, but it's not perpendicular. So the results that we derived till now are of no use. So we have to solve this from the basics only. Okay. The basic formula for moment of inertia of a continuous mass distribution is integral r square dm. Can one of you tell me what is r in this? What is the meaning of r?
So the distance from the axis to L.
Axis to?
L.
What is L? Anyone else? What is r here? Distance from where to where? Like in M1 R1 square, what does R1 mean?
The distance between the axis and the rod.
You can't take the entire rod, no?
A particle.
Particle. Okay. Like M1 R1 square plus M2 R2 square, so on. M1 is mass of the first particle. R1 is the distance of the first particle from the axis. Similarly, in integral r square dm, dm is the mass of element. R is the distance of element from the axis. Axis about which you want to find out the moment of inertia. Okay. So let's visualize the element now as usual. Consider an element from here to here. Let its mass be dm. Okay. R is the distance of element from the axis. Now distance of a point from a line. Axis is a line, no? Element is a point. Distance of a point from a line is always supposed to be the perpendicular distance. This is what you should call as R. Okay. Let's call this as R. We need to integrate r square dm to get the total moment of inertia. I is equal to integral r square dm. And in order to integrate this, you know dm should be expressed in terms of dr. This is where it gets slightly tricky in this case. Now, dm is the mass of an element. Mass of an element can always be written as lambda linear mass density, which is nothing but total mass by total length, multiplied with the length of the element. Okay, mass is lambda into length of the element. Now we have assigned the symbol r to the distance from the axis to the element. Then dr means the change in that distance. So dr will be this distance now. One of you tell me, is dr the length of the element? Or is the length something else? Is dr the actual length of the element? Or is the length of the element, which I have indicated in orange, different from dr?
Difference.
It is clearly different. Okay, you can consider this as an example if you want. The rod is inclined like this. Let's take an enlarged view of that element. Let's say the element is from here to here. Then this is the actual length of the element, which is dl. Okay, we are taking r horizontally, so dr will be from here to here. This is dr. They are definitely different. Okay, so same thing happens there also. So now we have a kind of situation here where we need to do something to relate length of the element to dr. Okay, we have to relate that slant length, which I have indicated in orange, to the horizontal length. For that, again, you can take help of this diagram itself. Slant length is dl, that's the actual length of the element. Horizontal length is dr. And you know that the rod is making an angle alpha with the y-axis. This angle is alpha. So can one of you relate dl, dr and alpha? Let me draw this line properly. It's very easy. There is a right angle triangle, as you can see. Angle made with the y-axis is alpha. So this angle will also be alpha. Relate dl, dr and alpha. In this right angle triangle, dl is the hypotenuse, dr is the side opposite to alpha. How are hypotenuse and opposite side related to an angle?
So dr equal to dl sin alpha.
Correct. Sin alpha is opposite by adjacent. That's all. So dr becomes dl sin alpha, or dl becomes dr by sin alpha. Rishi, Yusuf, Aishwarya, is this clear?
Yeah.
Okay. Now, where were we stuck? In integral r square dm, we needed dm in terms of dr, but we cannot directly write dm as lambda into dr this time because dr is now not the length of the element. Okay. So dm is lambda into length of element. Length of element is dl, which using trigonometry, we write dl as dr by sin alpha. That is dm in terms of dr. Okay. Now we are in a position to integrate then. I is equal to integral r square dm. That becomes integral r square. What was dm? Lambda into dr by sin alpha. Lambda dr by sin alpha. Lambda is total mass by total length, and sin alpha is same for the entire rod. The whole rod is inclined at the same angle. So I'll put them outside the integral. And what will you be left with? Integral r square dr. That becomes m by L sin alpha. Integral r square dr is r cube by 3. Okay. But we have to substitute limits carefully. Tell me, for the first element of the rod, this bottommost element, how much is r? Distance from the axis, how much is it? For the first element of the rod, how much is the distance from the axis?
0, sir.
0, it is touching the axis. So limit for r, lower limit for r will be 0. Next, for the last element of the rod, this one, how much is the distance from the axis?
L.
No, L is this length, no? This time that last element is not at a distance L. This we had discussed before also. You'll again have to use trigonometry. There's a right angle triangle here. For this angle alpha, L is hypotenuse, and you are looking for the opposite side. Again sin alpha, and this side becomes L sin alpha. So the upper limit or the final value of R will be L sin alpha. Okay, now you substitute the limits. Outside the bracket, you have m by L sin alpha. 3 is also there, you can put it outside. Inside the bracket, you have R cube, that is L cube sine cube alpha and lower limit 0. That's all. One L sine alpha and one L sine alpha will cancel. You will be left with m L square by 3 into sine square alpha. That is the moment of inertia of this rod, which makes an angle alpha with the axis. Or you can say that is the moment of inertia of this rod about an axis which makes an angle alpha with the rod. ml square by 3 into sine square alpha. Sine square alpha will be less than 1 only, no? So moment of inertia will be less than ml square by 3 as expected. When the rod is perpendicular, the moment of inertia was ml square by 3. When it is tilted like this, particles come closer. We expected the answer to be less than ml square by 3 and it is. Okay, is this clear to all of you? Fine. Let's revise what all we discussed till now in this class. So basically we are deriving the formula for moment of inertia of a continuous mass distribution in some cases. Okay, and today all the cases we considered were rods. The formula is integral r square dm. That's the basic fundamental formula for moment of inertia by definition. We are applying that to a rod. So first, uniform rod about an axis passing through one end perpendicular to it. Take an element, take the distance. Element is along the distance, so dm is equal to lambda dr. You can write directly. Substitute, integrate. You'll get ml square by 3. Okay. Next, we took an example and saw that moment of inertia can change from axis to axis for a given system itself. So for a rod about one end perpendicular to it, it is ml square by 3. That doesn't mean it will have the same moment of inertia about every other axis. So we took one more axis. Okay, before that we solved some problems, that's fine. Then we took one more axis which passes through the center of the rod perpendicular to it. And about that axis, when we integrated, substituted limits and all, we saw that it is ml square by 12. And we used another idea also to derive that moment of inertia. We considered the given rod as a collection of two small rods, one half, one half. Okay, why? Because for each half, if you see, this axis passes through one end perpendicular to it, for which we know the formula. That's why we took it as two halves. Okay, that way also we got the same result, ml square by 12. Fine. Then we solved some problems and then this final situation where the rod is inclined at an angle alpha. Okay. Fine, we'll stop it here because the next derivation again will be lengthy. It will take a lot of time. We'll stop it here for today, but I will be taking one more class on Sunday. Okay, we need to rush through your syllabus. I'll have to increase the number of classes. I'll take one more class on Sunday. It will be maybe 1.5 hours. Okay, full class. Timings I will inform. Mostly it will be in the afternoon this time. Maybe 1 to 2:30 or something like that. Okay, thank you all. We'll continue on Sunday.